Can you hear me?
Yeah, we can.
I'll share the sound from the computer. Okay. Even if you play this, still the same. Every call is of the same species. You can see the way, there's a variation in the call duration, etc. But of course, for any sort of temporal properties, use waveform. However, we have right now made about five selections. You can see five waveforms and five spectrograms. Wherever there's spectrogram, it is showing peak frequency and energy. Let me remove this maximum frequency. Okay. So now I want to get into some of the properties of the pulse. That is, for example, number of pulses, which has to be counted. So you have to first click on this table and add annotation column. Okay. So you have to add new column here. Means you're annotating a new column. For example, I will add number of pulses. Okay. See, you can click on the right click on the selection table, add whatever you want, because sometimes the software it will not measure it for you. For example, some values which has to be calculated manually. Okay. For example, pulse rate has to be calculated manually. Okay. I will add that. I will show you how to do that. Okay. And also maybe 50% call rise time, 50% call fall time, all that. I will show you for one call, but you can uh, continue it for others and do it by yourself. Okay. Maybe first let's move on to call characters. Let me delete this and add it towards the end. First, let's see what is called rise time and call fall time, maybe, if you're interested. But not very important. But I'll tell you what is called rise time, call fall time. Also, there's 50% call rise time, 50% call fall time also. Then we'll move on to some of the pulse properties. Pulses, number of pulses.
Sorry, Vineet, is that add column option only available in Raven Pro? Because I can't seems to be getting that.
Is it maybe
Add a
light doesn't have many properties because it's a beginner friendly this one.
okay, okay,
Maybe
okay,
once you get the license, you can do that.
okay, cool.
Yeah. So we can see pulse rate. Okay, let's do some analysis now quickly. Okay, then I'll make you do the other part of it. So let's zoom out a bit. This is one call. Okay, single call. So what is call rise time, call fall time? I'll tell you quickly. Call duration has anyways come. See, this is the call duration. This is the call duration. The duration of this call is 0.7647. Okay, one more value which I want is maximum amplitude. Okay, what is the maximum amplitude of this call? So if you see, I will add that here. I'm sorry, we need to add it to the choose measurement. Maximum amplitude. Okay, it has come here. Doesn't matter. So maximum amplitude of this particular call, that is the first call. What is maximum amplitude? I'll tell you again. Maximum amplitude is the amplitude which is highest. Like you can see there is a lot of different amplitude values. I can also mark it here. Here it is marked. So if I zoom in to this a bit, okay, it is showing which is the maximum amplitude. Okay, I'm not able to visualize it properly right now. So let's see. I think this is, yeah, this is the amplitude which is the maximum. Can you see here? This point, it has marked it as well. So this is the point where we have the highest amplitude value. Okay, let's try to keep it at the center. Doesn't matter. Okay, so I moved it by mistake. Not a problem. Okay. Now let us say that this is the maximum amplitude. I'm sorry. Yeah, let's zoom out. Let's say this is the point where we have the maximum amplitude, and we have to take the value from the starting till that particular point, as the call rise time. For example, from here to here will be the call rise time. But how will I know where is the value for that? You can see here, as I'm making this uncommitted selection, which is the 10th selection here, it is showing what is the time of that. Okay. This is 0.06436. This is the call rise time. I'll copy it here. Okay. What is the call fall time? From this particular pulse, which I told you now is the highest pulse, till the end will be the call fall time. Okay. From here, this particular pulse, which is the highest amplitude pulse, till here will be the call fall time. So I'll choose that value from here. So this you can manually do it. Okay. So anyways, I didn't commit those selections. I was just doing it for uncommitted selection. Till from here to here is call raise time. From here to here call fall time. Sometimes what happens is the calls won't be having very proper wave train. Okay. What is happening is it is rising suddenly and becomes flat. In that case, you have to take a value which is like the maximum amplitude, and other all values you have to exempt, and the last values which have 500 kilounits difference from that value has to be taken uh, as the highest amplitude. Okay, so whatever maximum amplitude is shown here, that has to be calculated, and then from the other side, you have to see where is the maximum amplitude, and the center ones you have to omit sometimes for call rise time and call fall time. However, it's showing here that one of the calls is maximum. I've taken this value, but it may vary based on your type of call. Some calls have same type of amplitude, so you cannot take the entire of that as the call rise time. Whenever you hit the first highest value, you have to take till then, and the last highest value until the end. That becomes call fall time. Let's move on to number of pulses. Number of pulses you need to literally count actually. Let's get into the first call and let's count. So this is the first pulse. Let me zoom in a bit. So you can see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48, 49, 50, 51, 52, 53, 54. Okay. 55, 56, 57, 58, 59, 60, 61, 62, 63, 64, 65, 66, 68, 69, 70, 71, 72, 73, 74. So this pulse, the number of pulses on this first call is 74. I'll add it here. What is pulse rate? I'll also tell you that. Pulse rate is from the beginning of the call till the last call. That means 73 calls are there, right? 73 calls. K is total number of pulses. I mean, I'm sorry, not call pulses. Total number of pulses minus one, that is 73. 74 is total number of pulses. 73 will be K minus one value. Just a minute. We need to calculate a value that is K minus 1 by time from the beginning till the last pulse. So from here till the last pulse. So what is the time? You can check here on the 13th measurement value, 0.7483. So 0.7483 is the total time taken from the first onset of first pulse, maybe till the last pulse, onset of, and can even move it from here because this is where we started at exact point. From here, just a minute. From this point, from the start of the pulse till the start of the last pulse. Okay. This is the time taken from the onset of the first pulse to the onset of the last pulse. and total number of pulses were 74, but the k minus 1 value, that is total number of pulses minus 1 will be 73. So 73 divided by this value, what is that? 0.7504. So that will give you 73 divided by, I'm doing it on my calculator, 7504 is 97.28. Okay. That means 97.28 or 97.3 pulses will be produced in a second. Okay. You know that this much pulses, 74 pulses were produced in 0.76 seconds. In 1 second, it will be able to produce 97.28 pulses. It's called pulse rate. Is it clear to you? Same way now, the pulse with the highest frequency you can take. Let's say this is the pulse with the highest frequency. I can zoom into that. This is how the wave looks like. This is called single pulse. Whatever pulse which has the maximum amplitude. Okay, see here, this has the maximum amplitude. You can even see the measurement bar is touching that. Of course, my cursor has gone a little off. It's fine, but let's not worry much on. Don't move this line because sometimes you miss the measurements. Okay, anyways. So from the beginning of the call, on a this is single pulse. What I'm showing right now is a single pulse which has highest amplitude. Let's say from the beginning of that pulse, okay, from here, let's say this is the beginning of the pulse. Then till that maximum amplitude is called pulse rise time. From that point till the end is called as still here because this is the silent periods. It's called as pulse fall time. This property also can take. See here, pulse rise time will be somewhat close to about 0. You can see the value 0.008, and pulse fall time from that point till the end maybe about 0.0037. This also you can add. So for every single call, you can take these many parameters. Okay? Please understand. You can take these many parameters. What is that? For the spectrogram, different properties. For waveform, different properties. So now, right now, if I take one single call, which we have analyzed, which is here, one single call, I'll zoom out into this. Every single pulse also you can see. If I zoom into too much, you can see pulse actually. See, ultimately it is a sound waveform, right? This was a single call which we analyzed. Just observe. So the single call which we were analyzing. Okay. And in that call, we found that the duration of the call, here this is the one, duration of the call is 0.7647 seconds. And the maximum amplitude was 21,000 kilo units. And then call rise time was 0.46, which took up to the maximum amplitude. Call fall time was 0.1136. Number of pulses was 74. Pulse rate. This is for one single call. Now imagine how many calls you have in this particular recording. You can do it for all. Wherever there is not much background noise, this is a very clean call. You can see that there's no overlap most of the time. There's no other individual who's calling. Okay. You can also see that there are some harmonics here, not to worry on that. But take all these calls which look for you that they're neat, you can observe them, you can identify them, you can write down the features. Okay. This is how you do the basic analysis of any call. You can now see that the signature of this species is it has 3617 uh, kilohertz, sorry, hertz, that is 3.6 kilohertz as the peak frequency. This is also a very important feature because this is like a signature for that species. If you see that based on the size of the animal, frequencies are going to vary. Now, this particular species is smaller, that is lesser than 2 centimeters. Now, I want you to open Microhyla ornata in your system and tell me what is the peak frequency of that animal. Let's see. And also Microhyla rubras, because Microhyla rubra is the largest animal. Okay. Rubra is the largest, followed by ornata. Let us see their frequencies. Can you do that on your system? Open the file, Microhyla ornata. Okay. And show me what's going to happen. What is the peak frequency at least? Let's do this exercise. This is the ornata call. You can see give me the peak frequency value. Can anybody give me the peak frequency value? One who has software. Just give me the peak. It should take not more than 1 minute. You can type it or on your mic and as well as you can say. You can already actually see here in the spectrogram what is the peak frequency. Where's the darkest band? Where's the darkest band? Does anyone have the software? Please check that quickly. I've already shared this calls with you. Not maximum amplitude, Deepak, peak frequency. That is maximum frequency what it is showing. 22,000 will be maximum frequency, not this value, not highest frequency. The peak frequency or the dominant frequency or the maximum frequency, which is frequency with highest energy. Like you can see a dark band, right? I can clearly see that it's close to 3 kilowatts, but I want the exact value. See, you can see from here the darkest region is somewhere here. Does anyone have the software? Like, or should I go ahead? Okay, no problem. I think most of you may not have the software. That's what I believe. If you have the software, you can please check it and tell me. The highest frequency is correct because highest frequency is the Nyquist frequency, what you're saying. That is 22 kilowatt. But what is the highest frequency of this call? Like, what is the maximum frequency or the peak frequency of this call? Okay, let us check that. Okay, I will select one of the calls. And what we did, we will activate the selection. It is active now. See, activated. And let's go to choose measurement and just click on maximum frequency, right? Maximum frequency and delta time. Okay. Yeah. Let's say okay. And you can see what is the maximum frequency of this animal. 3,100 hertz. That is 3.1 kilohertz. The earliest, this is what we saw, Sholigari, had 3.67, okay, or 3.7 close to. This one has 3.1. What do you understand from this? Is this animal bigger than Sholiga Naramouth frog or is it smaller? Can anybody reply in the comment? Is this smaller than Sholiga Naramouth frog or is it bigger? Probably, based on whatever hypothesis what I told you yesterday. Frequencies or pitch is lower than Sholiga Naramouth frog.
Bigger, because bigger the
Bigger, very
lower
good.
the frequency, bigger the frog.
Yes, very good. So bigger the size of the animal, larger the vocal cord. That's what I told you. Longer the thread, longer is the wavelength. Longer is the wavelength, shorter is the frequency. So lower frequency. As the size increases, frequency decreases. If you want, I can even check one more file. See, rubra is the largest of microhylids among this. I'll open this, and you can hear this count. There are two species. Whenever you are here is this particular sound. That is, see, this is ornate actually. This is rubra. Okay, I will play that together. You'll understand. Reddish narrow sound. Okay. This particular call is rubra's call. Let me slightly zoom into that. Okay. And you can see in the spectrogram here, two different calls. You can see even side by side. Let me zoom into that. See, side by side. What do you think? Which one has the lower frequency do you think? Is it Ornata? Is it Rubra? This is Ornata's call. This is Rubra's call. Of course, you may not be able to hear. This is Ornata. If I choose uh, max frequency or peak frequency, okay, and let's add delta time also. You will see both the calls, which one is longer, which one is shorter as well. Let's say this call begins from here to here, micro hello Rubra, and this call begins somewhere. Let me zoom in and see. Let's say this began from here. So the first call committed both the connection. First call is Rubra, second call is Ornata. You can clearly see the difference here. Third is anyways not committed. Look at only first 10 seconds. The first call has a peak frequency of 1119. What do you understand from this? Rubra is larger than Ornata. And look at the delta time of that. If the call is too short, 0.15 seconds, which is 150 milliseconds. And Ornata, the call is, as we saw even in the previous recording, 3000 hertz, and call is also longer. You can see just by the waveform and the spectrum itself that Ornate has a longer call. Okay, yeah. So you have already some calls. You can also record calls and analyze. This is how we do the basic analysis. So you do all the analysis. After that, you have to save this selection. For example, if I have done this work, let's say I have 100 different calls and uh, 10 different parameters which I've measured. Save active selection, okay, or save selection table one as. Okay? You can save it wherever you want, okay. Otherwise, it will naturally save in your C users folder. So you can use the same name, it will save. Okay. Active selection table one is uncommitted. That's fine. Third one is uncommitted. Yes, you do. Okay. Now it is already being saved. Now if I even if I close this all, okay, let's close all of this. Next time, if you want to start working, restart working on that, you can open the sound file. We opened, I think, Rubra. Let's open Rubra. See, right now it will not have any selections. And let's go on to the selection table. See, we open selection table. Open selection table. Okay. So open selection table. You can open what you saved. See that right now we saved. It will come and sit here only. See, already it came and sat on wherever we selected. So like this, your workflow will not be discontinued. Your workflow will be continuous. Means if you do not save your selection table, that selection table disappears the time you close it. That's why you have to save the selection tables once you're done. Even also, you can export it to Microsoft Excel and do your own statistical analysis, etc. in different softwares because you want these values. These numbers are very important. Number is a very important game in research. So if you want these numbers, you have to save selection table. Like again, I'm saying in file, save selection table one as. Then whenever you open the same file, again sound form or saved no, your data file, you can open that sound selection table. It will immediately come and sit in that proper locations wherever you are because it is having a data of begin time and end time. It began at 1.25 and end at 1.040. Second call, it began at 1.47 and ended at 1. That data is there already. That data is embedded. It will come and exactly sit at that particular position. Okay. So this is how you can do some basic analysis of the sounds very interestingly. This software helps you to analyze the sound. And later you can interpret this. Where this is useful, and quickly tell you. This particular method of studying sounds is useful in multiple areas. One thing is taxonomy. Means nowadays taxonomy is becoming integrative. You can't just tell that okay, this frog looks green color, it has this many patches, its hand is this big, leg is this big, and measurements are like this, SPL is this, head length is this, head width this. That's an older type of taxonomy. Okay, Now we have something called as integrative taxonomy, where you use multiple no, line of evidence to say that it's a new species or it is this species. For example, Microhala ornata, whenever you are describing, you have to give even its call characters, because without call characters, it's like incomplete. Whenever a species is vocalizing, you have to give even the vocal characters. For example, you found a new frog, which you think is a new species. You can do DNA analysis, you can do morphology studies, morphometry, you can do bone studies, you can do any sort of other analysis. But acoustics also is a very important data which you can add in your taxonomy paper. So taxonomy is today incomplete for taxonomy without acoustics. Second thing, what you can do is in cryptic species. For example, have you heard cricket frogs and let's say Indirana species? It's very difficult to identify them in the field using their morphological character. At that time, acoustics becomes a very important feature. So to delineate saying that, okay, I have recorded this species and I'm sure by analyzing I can say that how we can differentiate this. You can also write a paper on cryptic species and their calls so that for people, it becomes easy. For example, let's say Indirana Leafy has a frequency of 2000 kilohertz and Indirana Badrai has a frequency of 3000. That means you know that where they stand because of their body size and frequencies also vary. Okay, and duration of the call may vary, number of pulses may vary. That becomes a character for that species. So even in delineating cryptic species, acoustics play an important role other than molecular data, because you can't always kill an animal and look for molecular data and say that this is Indirana Lithi and Indirana Vadra, because it's just going to kill a lot of animals. This is a very non-invasive study. Just go and record the animal and okay, you say that I'm sure this is this particular species because I recorded the call and I analyzed and it's closer to or it's very much as Indira Nabadra. Okay, then you can say that this is this species only. So it helps in even identification of the species. Very very important. Okay. Third thing what we can do is we can do studies on how environmental sound, for example, noises, maybe aeroplane noise or traffic noise or maybe an industrial noise is affecting the sounds of animals. So you can record the same species in a natural setup and record the same species in a setup where there is disturbance. You can see that what is the difference in the record. Then you can propose that these environmental disturbances are changing the acoustic properties of this particular species. Okay, that's also one more application. And other applications could be evolution. You can also study evolution because sounds are also evolving. So some of them are working on called divergence. Also, if you see one of our good friends called Vaibhav is also working on how sounds of some of the toads in India is evolving. Okay, along with the evolution of the toads itself, how the sounds also are evolving. So there are a lot of people abroad who are working on the evolution, divergence of calls also. So other than that, you can also keep these recorders, what I told you, automated recorders in a place and get an idea what species are present. For example, you go on a walk and find out, okay, these many calls are there. Okay, this species, and make a list of 10 species. So if you know there are 10 species, you want to know after, let's say, about 10 or 20 years, is there 10 species or is it increased or decreased? You can keep an automated recorder, come back, and you can do the analysis because by the time next 10 years, already AI would have come, and you can even just with a click of a button, you would be able to say, no, just click that and say how many species are there. That would come because AI people are working on machine learning and artificial intelligence to identify call signatures based on the frequency and call duration, etc. They're also doing that. Okay, it will only tell you which species is that. That time is not far, so we can use it for even studying population density and what is happening to populations of species like birds or maybe frogs or insects in long run, just to also help in conservation also. So the scope is very, very diverse for acoustic field. It's up to you what you want to do and how it helps in your research or your studies. If you're an enthusiast, just record and for your own joy, you can also observe what's happening to the sounds and how do they look like, right? Yeah. Thank you very much. And if you have any doubts, please ask me now. So we come to the end of this 2 days certificate course or webinar on how to use the bioacoustics in amphibian research or amphibian studies, and overall, in general, also how we can use it for studying just sounds. Okay? If you are having any doubts, please throw it at me. If it is silly also, it's fine. If I know, I will definitely try to answer.
Thank you so much, sir. It was a lovely session and we learned a lot of things. And yeah, participants, if you have any doubts, please do ask. We have another 10 minutes. And the recorded session also will be shared with you. The certificates and all will be shared in couple of days. So now you can have a discussion session now.
Vinny, can we record in mobile and can you use this software by converting the file?
Yeah, you can
Or
you
is
can
that
use mobile. That's what. Yeah, you can get most of the data, but you need to record in a wave format.
so how to convert into wave format, like any software is there?
I
Or
think
any
you
like
have.
file we have to
Uh,
change the file name like anything.
I think you need to check which softwares are recording in wave format. There are, of course, I think I'm not sure because I've not tried recording in mobile. I think most of the mobile phones now, the recent mobile phones have wave format in it, so you can set it to wave format and record. Otherwise, you can download softwares which you can check for which has wave format in it and record it and analyze also. But you won't get a very precise, like maybe values, but it's still close
Hmm.
to the actual values what we do get even when we are recording with a sophisticated, unidirectional microphone.
Okay.
Deepak, you can even check Kohler's paper, which I've shared yesterday. He also shows in that paper how mobile recording and the sound recorder with the microphone, how it is, the values are different. And he says even using a mobile phone is good enough for any sort of uh, analysis. Yeah. Vivek has mentioned RecForge too. A file has
Yeah,
noises, how to avoid and continue analysis. Vivek, can you on your mic?
yeah. Recforge 2 app, we can record it in a waveform. But
Yes,
only
yes.
thing
Thank
is
you.
we have to record it in 16 bit.
16-bit, yeah. 16-bit is a little heavy on the mobile. I feel it's fine, like because nowadays your photos are large, so 16-bit is must. And also record in 44 kilohertz. That's also important. Vivek Gautam, Vivek.
I have one question like if during recording if we got noise from cricket insect
Hmm.
then um, if we select the from the active selection then it can shows the frequency of insect instead of frog, no? So at that
Okay,
case,
okay, that's a good question.
at that
So in that case, you need to first to see what is your, what is your recording? Is it having such insect calling throughout your call? Okay. If it is above the range of your species, it doesn't matter. Like, you can even sort of remove those frequencies by using low pass filter. You can use only the frequencies below that. Okay. You can even cut that part of the call. But if it is merging with your frequency, then you can't analyze because you have to record when that particular cricket is not calling. So to exemplify you, uh, crickets always call above frequencies of 5 kilohertz, and frogs, majority of the frogs in India call at frequencies below 5 kilohertz. So it should not be a problem for you. You can use a low pass filter and remove all that uh, part of the frequency which is above, let's say, 5 kilohertz.
okay, so where can we use a low pass filter?
You can use it, I don't know whether in Raven you have such an option. 1 minute. Band filter. 1 minute. I've not done anything like that. I think you should have some tools to remove additional noises. Otherwise, what you can do, one more method I can show you. Just listen here. I'll just show you the Raven once again. What you can do is imagine the cricket sounds are here. Okay, cricket sounds are here. You can only select from spectrogram and select only the call of your species like that for active selection. Let me show you a different part of the call. Let's say this is the call. You can record here, like like this. Make the active selection using spectrogram. Then you don't have any problem. See, fourth recording is only from here. You don't need to select this part. So if you select it completely from here, no, from the waveform, then you will have even this part being selected. As you said, it may show the frequency of insects. But since the insects are far most of the time, it will not choose that as the dominant frequency. Even if you see there's some insect probably calling it, if I'm not wrong. I don't know what is this, but it is not showing it is wrong. It's playing only the because it is very close. It's showing the frequency of this as a dominant frequency because it has the highest energy. When you record, it also takes the amplitude or spectral density values or the sound pressure values because the animal which is closest is the frog. It will not be taking the values from here. If you had recorded an insect and on the background frog was there, it would have taken insect call because insect call was very close to your microphone. Okay, so I think you shouldn't have any problem. Even in that case, you can select from the spectrogram instead of the waveform. Like you can select only from the spectrogram, then you shouldn't have any problem. I think there should be some option to filter out. There are some filters, but we need to check here. I've not used it. In Audacity, there's an option called noise selection. Okay. Audacity software. What happens is you can open your sound in Audacity and then choose that part which is for you is a noise. For example, maybe the cricket call is noise, and give the command that noise cancellation or remove noise. It will remove all that calls. That can be done in Audacity also. Yeah. Vivek, I hope I have answered your question.
Yeah, thank you.
Any
We
other
have
question?
2 minutes left, sir. If anybody wants to ask anything, you can continue. Or else, we have group. In the group also, you can ask your questions.
If two frogs are there, guys, if there are two frogs which are calling at the same frequency and they're merging, then it's a problem because they're close. Its frequencies are merging clearly, then it's a problem. But if they're at a higher frequency, it should not be an issue because you can select in the spectrogram only that part of the spectrogram which is your focal species. Yeah. You can always modify the spectrogram. Any other questions? Feel free. I mean, if you have any, even if you feel it is silly, it may be highly valuable question. We don't know. Okay. So feel free and ask.
Vineeth?
And one more suggestion to all of you is to record as much as possible clean recording so that you won't have much problem to edit it later because if you get a clean photograph, you know that editing is so quick. But if you get very noisy recording, you will invest a lot of time in noise removal and etc. So keep your recording clean so that you don't have much problems in the post processing or post analysis time. Okay.
Does the shape of spectrogram defines any characteristics, as in, like, we can see the low pitch one in the below range, right? Does it has to do
Mhm.
anything like the previous
Can
example
you
you?
can you can you repeat it, Anu?
So I'm saying the spectrogram, right? So it has this frequency low to high, right? When